Hello, everybody. So this is the IRM seminar. So thank you everybody for being here. It's our great pleasure to have Hamidreza Modares. He's an assistant professor at Michigan State. So Reza, he's a good friend and collaborator. So we graduated from the same university and we have worked in several projects together. So he got his PhD at the University of Texas at Arlington, and he has done some great work. We had, as I said, the same advisor, and he has done some great work through the years. And he's the associate editor of transaction neural networks and learning systems. So if you have any good papers, send them to him, and he will make sure that they have a fair review. And with no more introduction, I will be happy to give the stage to Reza. And please, whenever you have any questions, please write them in the Q&A session, and then I will read them to Reza. So thank you very much again, Reza, for giving the seminar.
Thank you very much, Kyriakos, for the introduction. It's my great, and thank you very much for inviting me today. So it's my great pleasure to give you this talk today. The title is Conflict-Aware Safe Reinforcement Learning, a Metacognitive Reinforcement Learning Framework or Learning Framework. And so here's the outline of the talk. I'll start with some challenges of reinforcement learning that we're going to deal with here. And then risk-averse reinforcement learning, metacognitive reinforcement learning, and some unified batch incremental learning. So, of course, reinforcement learning has shown impressive great engineering fit these last years, especially on simulated environments and a task that in a single task that must, or system that must operate in single environment, for which a specific pre-specified reward function, optimizing a pre-specified reward function, is going to provide or encode desired intention. However, like more complex systems, like safety critical systems that must operate in ever-changing and complex environment, optimizing a pre-specified performance function or reward function cannot guarantee both performance and safety across a variety of circumstances that they must encounter. And so to move from current reinforcement learning algorithms that are for simulated environments and single task systems to more complex safety critical systems that must operate in ever-changing environment. Actually, I believe that we need to shift from perfect rationality framework that optimizes expected utility of outcome to a decision-making frameworks that makes decision based on not only optimizing expected utility, but also probability of success or successfully or safely achieving assigned objectives. For instance, if you're facing with a new scenario or in which information gap or uncertainty is high, opting for high performance aspirations might not guarantee invariance of like safe sets, so means our confidence in successfully delivering safety specifications is going to be low. So therefore we need to design new frameworks that take into account probability of success when designing reinforcement learning algorithms. So here is the list of, the overview of the challenges that I discussed. As I said, performance and safety requirements of systems are context dependent, means the best control performance that the agent can deliver without violating safety depends on the scenario and complexity and even novelty of the situation. And that requires reward design depending on the context. And also, even if we have a good reward function, in the presence of aleatory uncertainty or randomness, if we just optimize the expected utility of outcome and ignore the variance, that can also jeopardize safety. And also, it can result in performance fluctuation, which is not acceptable for many performance critical systems. For example, if we just find a control policy that provides good performance in expectation, but it has high variance, some realizations you might get poor performance and with high fluctuation, which is not acceptable. So therefore, the research questions that here we're trying to answer is, in order to revise the reward function according to the context and situation, the question is how can we assess the limits of reinforcement learning and its competence, and depending on these factors, which determines how successful the agent can be, we revise the reward function according to the context. And another challenge is that, or question, how to make risk-averse decision-making mechanism, how to design risk-averse decision-making mechanisms without requiring any online interaction or exploration. Of course, online interaction or explorations sometimes it's impractical because data collection is either expensive or sometimes dangerous. So the question is, can we turn a large set of data collected offline into a risk-averse decision-making engine? So these are the topics that I'm going to talk about. The first one is that I'm going to start is risk-averse reinforcement learning. So basically, we can categorize reinforcement learning based on data collection. Three categories. I'm not sure if you can see this below. So this figure is taken from Sergey Levin's paper. So here, the online or on-policy reinforcement learning, actually, the policy that is under evaluation is the same policy that is applied to the system to collect data. And in off-policy reinforcement learning, actually, the policy under evaluation could be different than the policy that is actually used to generate data we use for learning. However, if there is a significant change between these two policies, we call behavior policy and target policy, then there's going to be huge variance in our estimation, even if there's no bias. So therefore, standard off-policy reinforcement learning, actually, even so we have a buffer of collected data, we also try to use collected data from very recent policies as well as the current policy. So it's a combination of offline policy and online interaction. Without online interaction, we're going to get a huge bias, variance, which is not acceptable. However, what's desired in many safety critical systems is that design offline or increment, maybe we can call it offline or batch reinforcement learning. And in this offline reinforcement learning, we assume that we collected data once, and after applying many control policies to the system. And then now we have, just like supervised learning, we have a batch of data available, and we're trying to learn the optimal control policy. Of course, this is highly desirable, but there are definitely challenges. And so here, I'm trying to just explain the challenges that we have in standard existing offline reinforcement learning algorithms. So the challenge is that in actually existing offline reinforcement learning algorithms, they use off-policy data, offline data, to either directly evaluate the cost corresponding to some probability distribution, some policy, while data is generated with some other probability distribution. So we either get bias or huge variance. Even if we use importance sampling to get rid of bias, we can still get huge variance if these two distributions are very different from each other. And even if we use it in policy search methods, policy gradient methods, so then data is being used for estimating the gradient, but the same issue is there. Even variance is huge or bias. So what we actually try to do is to provide batch reinforcement learning algorithms that are that actually are risk averse, means we are trying to minimize the variance as well. And in order to do so, we used entropic risk measure here, which is log of expected or exponential of the actual cost that you're trying to optimize instead of directly optimizing the cost. And of course, it can be shown that this cost is almost equal to expected value as well as the variance, and alpha is the risk factor that makes the trade-off between expected and variance. So now here, using this cost function, we are not only optimizing the expected value, but also variance. And our goal is to learn a control policy using offline data, such that we learn the optimal solution to this optimization problem. All right, so, but here's the challenge. If we write down the Bellman equation for a given control policy pi, and also the optimal Bellman equation, V star, as you can see now, because of this log expected exponential, this Bellman operator is no longer a linear operator, in contrast to standard risk-neutral reinforcement learning algorithms. And so, therefore, existing policy iteration, value iteration methods they rely on temporal difference minimization, least square LSTD, and those and LSTD and all those gradient methods rely on linear parameterization, so they're not going to work here because of this nonlinearity. So here, this is the main challenge. And I'll show you how we try to solve this using a different approach. But the first thing we did was we showed that those both operators, the Bellman operator and the optimal Bellman operator, they're contracting maps and basically, but with respect to some weighted subnorm. And the reason is that mainly standard RL algorithms, they assume the reward function is bounded, but for control task, maybe it's restrictive. So here we assume the reward function can be bounded by a function of x, w, instead of assuming that it's bounded by constant. And then we defined a weighted subnorm, and then we showed that now those operators, T, which is the optimal, and T hat, which is the Bellman operator, they're both the contraction mapping with respect to this weighted subnorm. And of course, based on this contraction and fixed point theorem, we showed that iteration on those operators provide the on the optimal Bellman operator provides the optimal solution, and iteration on the Bellman operator provides the value corresponding to a policy. But as I said, the challenge is that we have now nonlinear operators. Solving them is extremely challenging. So that in order to actually avoid that, inspired by linear programming based approach presented by Farias and Van Roy. Actually, here we try to, instead of solving iteratively that problem that I showed you before, so we try to actually solve. So this, instead of inequality, now we have, instead of equality, Bellman equality operators, we have now Bellman inequality. And now, of course, we showed first that this provides a lower bound, any solution to this inequality. And now, since we're trying to find the max over a lower bound, so the best lower bound provides the optimal solution. And since this must be satisfied for every u, therefore it's also satisfied for infimum, means that this is also equivalent to the optimal Bellman operator. And we showed this is convex. So now, and these two are equivalent. So here, but there's a challenge. The challenge is that it's an infinite dimensional optimization problem, and there are two sources of infinite dimensionality. One is V. V is our decision variable, and so of course we have an infinite number of x. So V could be infinite dimensional, so decision variable. And in terms of constraints, we have also infinite number of constraints. So the first step is just like standard reinforcement learning algorithms, we can use approximation of V using some basis functions. So now in terms of decision variables, we have a finite number of decision variables. That makes it semi-infinite, but still infinite number of constraints. That we'll talk about this later. So we actually showed that solving this optimization problem is equivalent to solving this, actually, where V star is the solution to the exact problem without approximation. So actually shows that it actually minimizes some weighted norm with respect to this C parameter. And another thing that we showed that the performance, we've provided also performance bounds guarantees. Well, actually, if in this inequality, V star is the solution to the exact problem with no approximation, and assuming that VP is the projection onto the subspace of span of basis functions, it means that if we select good basis functions, and if then V star can be very close to VP, which is its projection into the span of subspace span by basis functions. If this is small, but VP still can be an infeasible solution to the convex optimization problem. We need guarantees on the bound on the difference between the exact solution and the solution to the approximation here, approximate one-shot convex optimization problem. So we showed that we showed that if we have a good set of basis functions, and means if VP could be close to V star, then we can provide also bounds on the approximate optimal solution, but with respect to some weighted norm. And so here it shows how C and W comes to play. And so actually what's next we're trying to do is how to come up with systematic designs for C for given W, or maybe even W, and how W is related to risk of a given state to provide better performance bounds. So that's an ongoing part of the research. So the systematic design of these parameters to provide better bounds. But so once we learn V, by the way, this is just as you can see, it's so far we assume we have infinite number of constraints, and so but if infinite number of constraints are available, and if we can approximate V using basis functions, you can see we can get good bounds. And so data and once we do sampling, as you will see, so we can use a bunch of data collected offline, and we don't have that problem with bias and variance we have in standard reinforcement learning with importance sampling, as I'm going to show you next. So here, but there is one challenge. Once we learn V hat, if we're going to use this V hat to find the optimal policy, we still need to know complete knowledge of dynamics, because this X mu prime is the next state. So actually, implicitly dynamics come to play here. So to actually avoid this problem, we use the Q learning. So instead of V, we are now using Q. And now here we are sampling based on Q. So basically, Q has some, we are using function approximation for Q. So with decision variable is finite dimension. And also constraint, we are actually using here, as you can see, there are a bunch of samples that we collected, and then collected based on applying variety of different control policies to the system, and then based on these samples, we formed these Bellman inequalities. And now we have a standard convex optimization problem with finite number of decision variables and finite number of samples that can be solved efficiently using convex optimization tools. And so there's no need for importance sampling here. And of course, this convex optimization frameworks allows to do offline or batch reinforcement learning. And so, but of course, the number of samples is going to affect the quality of the solution. So therefore, we provided sample complexity analysis. But there's one challenge. In standard risk-neutral reinforcement learning, which is linear programming, in this paper, Farias and Van Roy, they actually used they actually provided a non-uniform sample complexity, which relies on VC dimension of the constraint space. But there's one challenge. VC dimension for LP stable, VC dimension for convex set is infinity. In our case, it's a convex optimization problem in general. So That's not going to work, sample complexity using VC dimension. And so another challenge with this non-uniform, by the way, by non-uniform, I mean that they try to show that any solution to the approximate problem is going to be close to the any solution to the exact problem. But the problem with this non-uniform sampling is that now the constraints are assumed to be sampled based on some expected discounted number of visits to state under optimal policy, which is unknown. So what's desired actually to come up with distribution independent sample complexity bounds. And so this distribution independent sample complexity bounds allows us to perform fully batch learning, because then samples don't need to be from any specific distribution, and we can provide performance guarantees regardless of how samples are collected, as long as they satisfy some IID condition. So actually, to do this sample complexity analysis, we have used a scenario-based approach. So based on this paper, decision making in uncertain environments, scenario-based optimization approach. And the basic idea in scenario-based approach is that we have a convex optimization problem where delta is some uncertainty and unknown, but it belongs to some set. So therefore, since delta is unknown, and it can take infinite number of values, so we have now infinite number of constraints. But as we know, like robust with respect to worst case scenario is very conservative. Instead, we can solve a chance constraint problem in which we try to make sure that with high probability these samples or these constraints are going to be satisfied for our range of delta. And so these chance constraint problems now, in order to get a solution for this, they showed that now instead of solving directly this infinite optimization problem, if we sample from delta, different values of delta here, you can see here, delta is being sampled, then actually solving this problem is actually the same as solving this chance constraint optimization problem. Means we can provide, we can actually show that with high probability, these constraints are going to be satisfied, and with some epsilon optimality condition. So basically, which is great, and of course, this epsilon and the probability depends, or the confidence test we have, which is beta here. If we're gonna improve, then we need more number of samples. So basically, this epsilon and beta probability of satisfaction depends on the number of samples. So, and so just since in our optimization problem it's the same thing, because we have an infinite number of constraints, but we don't have any actually delta there. Our constraints are being sampled based on just x, because let me just show you here. So we have only x that we are sampling from. But conceptually it's the same thing. So we use this concept, and we show that if we have this sample complexity, if this bound, then with high probability we can provide, we can guarantee that all the samples, all the constraints of the original optimization problem are actually being satisfied, while we are using only a finite number of samples to do the optimization. So another thing that we did actually is we also extended this framework to the value iteration. And the reason that we use value iteration is the previous one was just one-shot optimization problem, because we just needed to solve, we needed to collect a bunch of samples and then solve a convex optimization problem once. But of course, we need a rich set of IID data in order to get good results. But if we don't have the luxury of availability of rich or large number of samples, then maybe we can also use online interaction as well as past data. So that's one reason for using value iteration, because while iteratively using, updating the value, we can also collect new data. Another reason is that when we are using value iteration, since this is from past values, As you can see, this is new, this is past. So now this used to be convex, but now it's known. So in terms of decision variable, we have just this part, which is linear now. So this makes it an LP or linear programming instead of a general convex optimization problem. And we show that this converges to the optimal solution. And another actually approach that we did is policy iteration. So advantage of policy iteration is that we can, as we showed in the paper, we can guarantee that consecutive control policies are asymptotically stable or stochastic asymptotically stable, and this is what we've shown. And in value iteration, that's not possible. But so as you can see here, we iteratively find value functions, but here, so in the one-shot optimization problems, we had freedom in choosing states and actions, but here actions are coming from specific control policy that is under evaluation. However, we show that we can also include binding constraints from the previous data collected from previous policies, while still guaranteeing that we improve the value at each iteration. So that makes it off-policy reinforcement learning. But the advantage here, of course, it becomes now convex instead of LP in contrast to value iteration, but it provides us with stability guarantees. So stimulation that we did actually here, as you can see, for a simple system that we did the simulation, a linear system. Here, as you can see, this is for like 100 number of experiments and different. As you can see here, as this is a number of samples. As we collect more number of samples, the blue one is the optimal. As we collect more number of samples, we get closer to the optimal solution, as of course as expected. But the other thing is that, as you can see here, we did the experiment. This is the trajectories over time. And again, for 100 different experiments, but the blue and red are actually the average one, the expected one, average. So as you can see, red one is a neutral. Blue is for risk-averse. In expectation, the red is better, as we expect, because here in the risk-averse, we are optimizing expected value as well as variance. But as you can see, the variance for the risk-averse is less than the risk-neutral. And if you're going to get even lower variances, we need to increase alpha, but that comes at the cost of decreasing the expected value. So now the second part is the metacognitive reinforcement learning algorithm. And so here, I'm going to quickly review existing safe reinforcement learning algorithms. Actually, in safe reinforcement learning, we're trying to solve a constraint optimal control problem under uncertainty and dynamics. So optimizing this cost while assuring that the system state never enters some unsafe set when starting from any initial condition inside some safe set. However, solving this optimization problem is a daunting challenge under presence of uncertainty. Therefore, most of the existing reinforcement learning algorithms, what they do is they first solve an unconstrained reinforcement learning algorithms, optimize this cost while ignoring constraints, and then they design a shield based on mainly reachability or barrier certification methods to assure that the action of the RL agent before applied to the system is safe. And they try to minimize the intervention, but intervention minimization is myopic, so in the sense that they don't optimize the accumulated intervention, and that can completely destroy the performance of reinforcement learning agent, especially in situations where in systems that scenarios can keep changing, and some scenarios might, in some scenarios, some high performance maneuvers might be in a great conflict with safety specifications. Therefore, the shield might need to keep intervening with the RL agents to fix its actions. So that's you can see this better here in this example. This figure is taken from this paper for a different context, but similar. So here it is shown that, for example, if steering actions are designed for some specific environment like this, now if the and let's assume that this is designed based on some reward-based learning, like end-to-end learning or whatever. And then if the environment slightly changes, now assuming that RL agent designed these steering actions without considering safety specifications, then of course the shield can provide safety. It can make sure that it never gets off the road, just like this. But as you can see, it's going to keep intervening with the actions of reinforcement learning and completely ruin its performance. Instead, if we actually design a new reward function, because reward function determines the priorities that we have over different performance metric that we encode in the reward, right? For example, a comfort, jerk, or tracking error or control effort. Like if we change the preference for or safety specification, if we change the preference, then the behavior is going to completely change. So what we actually propose here, instead of completely reactive and myopic intervention, so we try to do it in two levels intervention with reinforcement learning. So that's based on dual process theory of human thinking, and it says that actually human has two levels of two systems of thinking. The first system, which is system 2, actually is proactive. So it proactively monitors high-level specifications. Actually, here we assume that it monitors some task-agnostic specifications that determine a corridor of correct behavior that actually shows whether reinforcement learning agents is functioning as intended. And in order to actually determine those specifications, we are using signal temporal logic. So signal temporal logic here provides a corridor of acceptable behavior based on some prior knowledge, some rules, and some goals that eventually the reinforcement learning agent must achieve. So by proactively monitoring these specifications, then we can determine if the reward function is in great conflict with this specification. And if it is, then this monitoring metacognitive control is going to revise the reward function of the lower layer. Then we also have a lower layer reactive controller, which is going to be fast and reactive. So this is proactive and usually slow. The system 1 is fast and reactive. And so basically system 2 learns what to achieve, because reward determines what we're going to actually achieve, depending on the scenario. Because in different scenarios, we can achieve different performance specifications safely. So that takes care of this part. And here the lower layer learns how to actually safely achieve those assignments. So we use as I said, the signal temporal logic to specify corridor of acceptable behavior, and signal temporal logic of course provides quantitative semantics as well, and it determines not only if the specifications are satisfied, but also how well they are satisfied or how close they are to being violated. So now, basically, we have temporal logic specifications, which could be task agnostic and general, but also we want to have quantitative performance criterion that can include more subtle considerations like tracking error, like comfort, and so on. So we have this reward function based on numeric reward functions. So of course, STL can be combined, and we can convert STL into reward function and use it here. But then we need, as you know, most of reinforcement learning algorithms for temporal logic specifications, they use a Bokeh automata or some sort of automata to for the specifications, and then they form an augmented system based on the Bokeh automata and the actual, usually MDP system. So that increases the computational cost. So instead, we actually separated them. We only monitor specifications as we assume these are corridor or acceptable behavior. We monitor, and whenever they're about to be violated, then we adapt this numeric reward function that determines how much performance we can deliver without violating these specifications. So we defined some fitness function, and we showed based on the robustness of specifications. And we showed that actually we also defined some viable set, and the viable set is the set that actually there is a controller that satisfies all specifications. And we showed that if there is a viable set, then the fitness is going to be bounded, otherwise it grows unbounded. So therefore, monitoring this fitness function is going to tell us whether the lower layer reinforcement learning is doing as intended. And so in order to just use a single trajectory of the system while learning the fitness function, we used like just simple inspired by temporal difference learning. We used now this equation, but in order to also provide the confidence that we have on our estimation, we use the temporal difference Gaussian processes. And also, in order to transfer learning in different contexts, actually we use the shared covariance function. So in this covariance function, if you can see, the first part captures similarities between different states, because different states that are close to each other, their fitness or vulnerability is going to be almost the same. And that's for reward parameters. And that also captures some some parameters that determine the context but can be measured or previewed. For example, curvature of road or for example, road boundaries, all those or inclination. So any information that can be previewed by using sensors. So we can also incorporate them here, because if they're similar to each other, we are expecting that the fitness is going to be the same. So we don't need to do the data collection from every scenario and redo learning of the GP this way. And another thing that we did actually is we actually combined few-step near future forward prediction and distance future permanent. So what I mean is, because in STL formula we have a horizon because of temporal operators that we use in STL. So for that horizon, we actually try to monitor. We actually try to measure this directly. Means a few steps by. Actually, this can be done by forward simulating the system. Because forward simulating the system, we can measure the robustness values and then this term. But since we assume we don't know the dynamics, we actually used formed a Hankel matrix of the past data, past current data, and then we showed that we can span the entire future trajectories of the system, given actions of the reinforcement learning. So it means this near future can be found based on Hankel matrix of data, and then for this we use the temporal difference learning. So that's the schematic here. Given current trajectories, using Hankel matrix of data, we can predict the future trajectory within some horizon that could be a STL horizon, and then we can, of course, determine this part. And we use Gaussian processes to actually provide fitness or vulnerability expansion over the states that we haven't even seen or visited. And based on those specifications, we actually adapt the reward function. And so once the fitness is below some value, actually we use the safe Bayesian optimization to make sure that the fitness, unexpected value of fitness is always below some desired value, while we are that the reward parameters are as close as possible to some desired values. And so for the lower layer, I'm going to, for the sake of time, skip this part. So we used, for the lower layer reinforcement learning, we use some off-policy or reinforcement learning, so that allows us to actually learn simultaneously, as you can see in this equation, simultaneously for a given control policy KI, simultaneously we can learn PI and the next policy KI plus 1, as you can see here, and just using a batch of data available from some behavior policy, because this is very critical, especially when there's meta-learning. There's a meta-learning layer, and we want to make sure the lower layer learns as fast as possible the optimal policy corresponding to some reward values. So in terms of simulation, so we did it assuming for a lane changing, assuming we have this linear system. And the reason we did it linear is off-policy, Bellman, doing off-policy for low layer for linear is very effective, even if the policy that is applied for data generation is far from policy that actually is being evaluated. That's going to give us the exact same, the optimal solution. But for nonlinear systems, theoretically, we get the same results, but in terms of simulation, it's really hard, and they still don't know why. So therefore, we actually did a linear system here because of the lower layer. And so here we assume, actually, as you can see, in normal scenario, it works perfectly. And and this is actually the robustness values. So, but if there's a change in the dynamics and the system still relies on the previous reward function to learn control policy, as you can see, then it starts oscillating, and even at some point it can violate safety. Of course, we can use reactive methods to make sure it never gets off the lane, but still it's going to show these oscillations. However, if in our upper layer we determine that oscillation of temporal logic specification is not desired, then it's going to realize that this is not acceptable and it's not as intended. And that's, of course, robustness degrees. Then actually we showed that just by adapting but by the way, this was an LQR problem, by adapting the relative importance of different weights in the Q and R, it can actually, as you can see, performs much better. And of course, this can also be fixed if we include more performance metrics in the cost function. But we just wanted to show that it changes the behavior, and then and of course, transfer learning is also possible because of this shared covariance that we use. So therefore, it makes it data efficient, and it means that as scenario changes a little bit, we don't need to relearn the entire Gaussian process and do the learning again. So it means we can quickly find a new reward function. So I think I have 10 minutes. Okay, so now in order to do reactive actually making, so proactive was the upper layer. So in order to do reactive decision making, actually what we did is, okay, so as probably you know, safety could be in conflict with stability, even if we assume we don't have that reward function or cost function. Now we only care about safety and stability, but these two, for general nonlinear systems, safety and stability can be in conflict, and so we need to sacrifice most of the time stability for safety, and that can cause some issues. However, if we learn a linear representation of the nonlinear system using Koopman, then of course, then for linear systems, and assuming that the safe set is a C set, which is convex and compact, then of course we can use the concept of lambda contractivity to bring together safety and stability. It means we can find the Minkowski function, which is actually a Lyapunov function, that satisfies both stability and safety at the same time. So we don't need to worry about conflict between safety and stability. So therefore, we came up with a learning a coupon operator for the lower layer, and then because of its linear representations, we can do both safety and stability for reactive part. So, but the challenge is that most of actually, I'm not aware of any, but the coupon identifiers are using batch learning, means they assume that there's a batch of data available, and then they use PAC, probably approximate correct sample complexity, to provide bounds on the learned model or the performance. However, this sample complexity analysis requires a huge number of IID samples to guarantee generalization across unseen states. And again, it relies on a VC dimension of search space. On the other hand, of course, we cannot wait until we collect enough or reach number of data to make decisions. On the other hand, online learning provides learning. Actually, we can learn the model as the data becomes available. So, which is great in this sense because we can make decisions on the fly. But the problem is that we can provide guarantees on parameters only under restrictive and also hard to verify persistence or excitation conditions. So therefore, we try to provide a unified batch online learning framework to carry the strong generalization guarantees of batch into online learning, and without requiring this restrictive IID sample condition. And of course, we try to also provide finite time guarantees, because when it comes to safety guarantees, if the lower layer, if for the lower layer model learning, which is used for reactive certification, if it takes a lot of time to learn, that's not acceptable. And also, it will quantify uncertainty on the learned model, which is very useful, and it allows us to do non-conservative safety certification, because if you have quantification on the uncertainty, we don't need to do worst case analysis. And also, we try to learn both the structure and parameters of coupon operator. So just due to time, I'm going to skip this. So basically, so if we assume that this is in coupon operator, actually we try to find a set of observables under which the flow of the system actually evolves linearly. As you can see, the system evolves linearly as A and B. These are linear dynamics. But since we are trying to use finite number of observables, that this observable lift, or actually we do transformation from X to Z. Now we have a linear system. Since we're trying to do it with a finite number of observables, there's going to be, most of the time, there's going to be approximation error. So we assume this is approximation error. So now, if I assume this is the learned model, and these are now the parameters of the actually coupon operator. So here is the update law that actually we provided. Basically, this is based on gradient, but we actually modify the gradients. We provide the discontinuous gradient flows because we want to guarantee finite time convergence. And we also modify gradient in the sense that we are not only using current data, that's current data, but also past data in our update law. So another advantage of this approach is that actually basically in order to use gradient, so if you use standard approaches, then we end up requiring the derivative of the states, the lifted state actually, which is not available and hard to measure. So therefore we used a filter regressor here. We provided a filter regressor that shows actually here, as you can see, it shows how the lifted states are going to be linearly related to regressors, but these regressors are not static. They're time-varying regressors, and actually, as you can see, but they vary based on some dynamics which are known. So this is completely known. The only unknown is going to be this part. And this resembles like a regression problem. Now we can use the gradient descent, but gradient descent, not just as you can see here, that's the gradient part, and not just for the current samples, but also past samples in the history of that we actually selected and we stored in some memory. And we show that if the rank condition on these collected samples, if the rank condition for this matrix is satisfied, then it guarantees finite time convergence. By the way, this is the ceiling function, because it means that it's discontinuous. And so we showed that actually convergence is guaranteed with prescribed settling time. And the settling time, as you can see, also depends on the quality of the data that is, the batch of data that is stored in the memory. So basically, before the rank condition is satisfied, before the batch of data satisfies some, by the way, rank condition is easy to verify. Before the rank condition is satisfied, we can only guarantee that the tracking error is going to go to zero asymptotically. Means there's no generalization guarantee. But after the rank condition is satisfied, then there is also generalization guarantee as well. Means we can that we can definitely guarantee that not only the tracking error, but also the estimation parameters converge to their actual values. And so this was assuming that there is no approximation error. For the approximation error, we also showed that in case of approximation error, in this case, we have a UUB guarantees, but we showed how the bounds can be decreased based on the quality of the collected data in the batch, in the memory, collected or batch of data in the memory. And of course, we don't need any IID sampling here. It's based on some only rank condition, which is easy to verify. And also we did regret analysis. I'm gonna skip this because of time. And another advantage of this algorithm, first of all, now we have a Koopman learning that is actually guarantees that converges to zero in finite time. But if we don't select the right set of observables, we might end up with corrupted dynamics, means it's not even possible to get a good approximation because of the observables. So now we define some meta cost, which is the cost actually, that's the performance of the learned model on this could be the actually data collected in memory, as well as the cardinality or the number of observables that actually we are going to select. As I said, a good advantage of the proposed approach, the lower layer, is that the lower layer now allows us to evaluate this guy using only samples that are collected in the memory. Means we can do evaluation of observables using only off-policy data. Of course, we can also include online data, but that makes it control agnostic, means it doesn't, the quality of the learned model does not depend on the controller, which is critical because, of course, we know if it depends on the control, then the quality of the data collected from applying different controllers could be different. So, but here, since we have a memory of batch of data, which provides a good representation of the entire search space, because after the rank condition is satisfied, then we can do a fair comparison, and then that's the meta layer that actually uses Bayesian optimization, discrete Bayesian optimization, because now we have discrete decision space for the observables. And we did the simulation for a simple nonlinear system that has this Koopman representation. So we assume that we don't know the observables, so we use a library of observables, as you can see here, 9. And we showed that, of course, different set of observables, we end up with different errors for the identification. And then using our Bayesian optimization, we found the best set of observables that provides, in this example, no approximation. And this shows convergence of parameters fast and in finite time to their optimal value. So, and I'd like to thank my PhD student that contributed this work. And now I take questions. Thank you very much.
Very impressive work, Reza. Thank you very much. Any questions from the audience? Please write your questions in the Q&A. So, when you used, I saw that in your learning approach you had also, you can have time constraints. How do you take care of the time in an infinite horizon sense?
Okay, so that's a good question. Let me just go back to. So the first point is that we only use these STL just to monitor. We don't directly use them in control. It means controller is not designed to satisfy STL specifications, because as you know, in this case, you need like Boki automata for a specification, and then it must be augmented with actual system. So we don't do that. We don't do augmentation because we use only STL specifications for monitoring if the system is functioning as intended. And then, so but still there's a horizon of for STL formula because time is involved. That's why actually for the first part, for the few step near future, we do forward prediction using Hankel of current available data, because that Hankel of current available data allows to span the entire future given a set of actions. So for the means for this provides also some sort of reactive actions, means that if this few step near future predicts that STLs are not going to be satisfied, so we do forward, then this can provide some reactive mechanism. So the point is, we don't design controllers to satisfy specifications. We use STL specifications to monitor function.
I see.
That's because of course you know that designing the control directly satisfying a specification is definitely computationally challenging, and that's why we thought this could help us to use these specifications to monitor them, then to actually provide some vulnerability sense of assessment, how vulnerable the system is, and based on vulnerability, we adapt the reward function to the context.
I see. And then one more question. So when you do the chance constraint optimization, do you tune the Gaussian functions? Do you use Gaussian functions for the chance constraint? How do you do that?
So Gaussian function, yes. So but we try to minimize the frequency of adaptation learning of the Gaussian function by designing shared covariance matrix, in the sense that so this is some factors or some previewed information, some information that we can preview using sensors like curvature or like inclination or some road friction, anything that we can measure. And so based on similarity of the context that we have seen before and the current context, so we can come up with a good prior, and which tries to actually satisfy those specifications as much as possible, but then we fine tune it.
I see. So you don't, you start with a mean and a variance, and then you continue with this mean and variance.
Yes.
But as you go, okay, I see. Yeah, so I will talk to you offline about, I wanted to also do something on that, but how that you tune your mean and variance in your chance constraint optimization.
I'll be happy to talk. Yeah, sure.
Yeah. So any questions from the audience? Let's see. So it seems that everything was really clear, Reza. And so thank you very much again. Thank you for giving this amazing talk. It was very, very descriptive, very nice. And I'm sure I'll get back to you for some collaboration things. And yeah, and then again, thank you everybody for attending this IRIM seminar. And the seminar is recorded, so I'm sure if you miss something, you can go over again, or you can email Reza or me, and then we can set up some meetings or discussions. So again, thank you very much, Reza, and I'm looking forward to see you in person, and we will be in touch. So thank you very much again.
Thank you. Have a good day.